Okay, I think we'll start. Welcome to this talk about fuzzing with AFL. This will be a kind of introductory talk to fuzzing, so if you're already an AFL expert, you won't get that much out of it, I think. A little bit about myself. I work at a company called Blank in Oslo. I usually do development, but also some security testing, security architecture, bug bounty stuff, and I build open source security tools. And I'm also head of the OWASP Norway chapter. I had been wanting to get into fuzzing for quite some time because I had a lot of colleagues and friends that were doing fuzzing, but I never really got around to it until I did an online course, I guess about a year ago. It was two guys from Lift Security, and they did an online training about fuzzing native Node.js modules. And that really inspired me to get started with fuzzing, and it's actually quite fun to do, and it's something that can be really useful for making robust applications. So the problem with testing, when we normally write tests ourselves as developers, we know the code. So we know what the code is supposed to do. And we kind of tend to think in that way when we write our tests. We write a lot of happy path tests, and then we try to be smart and clever and write some tests that test the edge cases, but we tend to forget some things. And then we have the testers, and a lot of testers, they are quite smart at doing all kinds of edge cases and weird things like this. But they don't necessarily know the code, so they don't know what the code should do or could do. So or some of them do. Of course, there are different types of testers, different types of developers. But again, we're going to test a set of the actual inputs. We might have some ugly code like this, and the more branches we have, this might be deep down in some parser somewhere. And we might have a lot of different branches. So if we were to draw out the entire set of branches in our application, it would look something like this, because there would be a lot of different ways that we could get to different paths in our code. And what we want to do is try to test as many of these as possible and see if we can make our application crash in some way. And this is what fuzzing can help us with. Often we use code coverage as a way to figure out how much of the code that we've been testing, but code coverage is not necessarily the same as path coverage. Like the lines might have been marked as green, but we haven't tested these two green bits at the same time. We might have tested one of them in one test and one of them in another test, and we don't necessarily know that we've tested everything. So this is why code coverage is not necessarily a good measure for how well tested our code is. It just tells us which code isn't tested. So fuzzing. Fuzzing is generally the idea of throwing a lot of input at an application and see how it responds. So we could do this all night long if we can get a computer to do it. So Craig Young, who's done a talk on AFL earlier at B-Sides, he said you can find bugs in your sleep because you don't have to do it anymore. You can make the computer do it, which is nice. And I've been doing this for quite some time now, finding bugs in my sleep. So basic fuzzing, we could just take dev random and pipe it into the application and see what's happening. And this might actually work for some applications, but it's also kind of a stupid fuzzing, because if we get a crash, we don't necessarily know what caused the application to crash. Which input was it that made the application crash? And we might run the same thing all over and over again. So we might get hard to reproduce bugs. Like we knew the application crashed at some point during the night, but we have no idea what was going on. So we can get some smarter fuzzers. So we can get a mutational fuzzer. And a mutational fuzzer will take a valid input, like a valid file of some kind. Like if this was an image parser, we could take a valid image. And then we could flip bits or relocate data within this image and see how the application responds. This is, of course, a lot more effective than random, but we still have no insight into what's going on inside the application. We might try the same thing over and over again, and so we're fast and we're trying and we're testing, but we're just testing the same thing. We don't know what's really going on inside the application. There's also something called a grammar fuzzer, and with a grammar fuzzer, we're typically then testing the application with some type of grammar. This could be a protocol, or this could be a way to handle some type of text or input of some kind. And then we have to kind of define rules for how this input can be changed, and this can be really good for like really structured data, but it can also be quite hard to get it right, because we need to have a lot of knowledge to build and configure the parser correctly. So what if we could just have a fuzzer that would look inside our application and then apply inputs at the same time? That would be really nice. So we wouldn't have to come up with everything up front. So we have something called a feedback-based fuzzer. So with the feedback-based fuzzer, we're going to use coverage. So we're going to compile in or add in instrumentation into the application. And so the fuzzer can talk to the running binary and see which branches are being hit. And then it can mutate the input, and then it can see what happens if I mutate this input. And by doing that, it can know when it's doing the same thing all over again, and it can stop doing that, and it can start mutating something else instead, which makes it a lot more efficient. So this is a bit slower because we have to have the instrumentation in place, and we have to compile things and do things in a little bit of a different manner. But of course, the effectiveness is higher because we're removing all these repetitions that we might be doing if we were just doing like one of the other types of fuzzers. So the best result we get if we actually compile the application. We have the source code available, and we compile in the instrumentation. But we can also, with AFL, we can add it later to a binary if we want to. So AFL. AFL was developed by a guy called Michael Zalewski, who works at Google. His inspiration for building it, I think, came from some stuff that Tavis Ormandy of Google was doing. And it's open source, and it's quite cleverly made, I have to say. I'm no C or C++ expert at all, so I can't vouch for the code, but I've been using it to test code, and it's, let's say, highly effective. And this is a Hall of Fame from the AFL website, where there a lot of these, like you can see Firefox, you can see iOS kernel, you can see MySQL, you can see all kinds of applications and OSs and things like that, where AFL has found vulnerabilities by fuzzing. So it has quite a good reputation for finding hard or finding bugs, basically in everything that's written in C or C++. This picture is from a blog post written by the author of AFL, where he created an empty file, or not an empty file. The file said hello. That was the input. So it wasn't a valid JPEG. And then he started fuzzing that file with a JPEG parser. And eventually, because AFL is so smart, it would eventually start producing valid JPEG images, just starting from the string hello. So we don't have to even give it a valid input. But of course, that makes it faster if we can give it a proper startup. But we could just give it an empty file, and it would actually eventually figure out how to make, in this case, a valid JPEG. Installing it is fairly easy. You just download it, compile it, and it's super fast. It's small. I think it's like 53 kilobytes or something. And then you have what you need. You might need some dependencies here, like if you're going to use the LLVM mode, you need LLVM config and things like that. But it's generally really fast to download, install, and then you're up and running. You can fuzz things that are non-x86 as well, because the instrumentation in LLVM mode is supposed to be CPU independent. I have never tried it, but I know a lot of you are probably working in the embedded space, so it is supposed to be possible to fuzz things that aren't x86. So the workflow of fuzzing something is we need to compile the binary, or we could instrument an existing binary, but usually I will compile the binary with AFL. I will then find a test corpus, like a set of test files that I can use. I'll run the fuzzer, which is, of course, the thing that takes the most time. Then triage the findings, figure out what was happening here, what caused the crashes and things like that, and then maybe there's some profit at the end. But before all of this, we need to get some hardware. And when I wanted to start to fuzzing, I was thinking, well, what kind of hardware do I actually need? And usually it's good to have like a multi-core CPU and a decent amount of RAM. So I started poking around, and I asked some friends, and they said, well, you cannot use like a cloud VPS. You can't go to DigitalOcean or AVS and then just buy a VPS, because they usually don't allow you to run at 100% CPU all the time, because of course they overcommit on CPU. That's a part of the deal. So if you run your VPS on 100% CPU for an extended period of time, they're going to reboot it. And eventually, if you keep doing that, they're going to kick you out. So what I did instead, I went to a company called Hetzner, and I rented a server there. And I'm paying, I think it's 20 euros per month for this, which I think is a fairly decent price. I was actually thinking of buying something and putting it in my house, but then I saw the prices here, and because what they're doing is like they're taking servers that have been used by their clients that are not using them anymore, and then they're renting them for a cheap price so you can find something there. I actually paid more, but then I found a new server that was exactly the same specs, but with a cheaper monthly price, so I switched recently. Next, you have to compile the binary, which is also quite easy. You're using the exact same commands as you would do for compiling a standard binary. The first thing you do is you tell it which of the compilers you want to use. So AFL comes with, I guess, 6 different compilers, but there's a GCC compliant one, and then there's a CLang, and then there's CLang Fast, which is the LLVM one. And that's generally the best one to use if you can. There's something called AFL instrumentation radio, which tells it how much instrumentation do you want to add to your code. And usually I set this to 100%, but you might want to change it if it's too slow or if it doesn't find anything for an extended period of time. You could also set AFL harden, which is also something I recommend you do, because this adds some code hardening, so you can provoke crashes quicker. So it adds stack canaries and things like that. Once you found a test corpus, which is what I usually do, is if I'm going to fuzz something I find online, I go to the GitHub repo and I find a test folder and I grab the files there because they're usually a good set of test cases, and I use those as the corpus. But once you found that, you probably want to minimize it, because the larger files you have, the slower it will go. And of course, if you have a lot of files that are essentially the same, that won't help you either. So AFL comes with 2 tools for you to use. There's something called AFL cmin, where you can take a lot of a list of files within a folder, and you can tell it to minimize this list, so it removes all the things that aren't interesting. And then you can minimize a certain test case with tmin. So you basically, it will chop off things and normalize bits and try to figure out what's the smallest file I can use where I still get the same code coverage. So it's pretty smart about that as well. And then you can get a small set of files which are small, and that will make it run fast. Once we run the fuzzer, on the top here you see a single fuzzer running. Where you specify the folder name, where you have the test cases, you specify an output folder, and then you can specify options if you want to. And then you specify -- and the binary and the options to the binary. And then the at the end means that it's going to take input from a file, because you can also use AFL with input from standard out if you, or standard in, I guess, if you want that. In the second block here, you see me running a fuzzer in multi-core mode. So I have a master, which is the one with the -m at the top, which is fuzzer 01. And then you can add slaves to it. They all just have to point to the same directory. And that works perfectly as well. And that's probably what you want to do if you're going to fuzz something that's big, or if it's slow, or just generally if you have enough CPU for it. You can specify some options. There are a lot more of options that you can use, but the normal ones are -m for how much memory do you want to limit each test case to use, or each run of the application to use. So it will crash if it's using more memory, or getting out of memory. You can also specify a timeout, because you don't want it if it's hanging for an extended period of time. Maybe you're doing something and it goes into a while loop or something that it never exits from. So you can specify how much time, what's the maximum run time for each of these runs. Or you can just let it figure it out itself. This is the interface that you get. It's very ASCII, or ANSI maybe. I'm going to get back to this in a little bit, because we're going to do a demo, but this is basically the way it looks. Once you start running it, you get an output folder, one for each of the fuzzers. So if you're running like a master and 3 slaves, you're going to get one folder for each of them in the output folder. And inside there, you're going to get one folder that's called crashes. This is where inputs that cause the applications to crash will be. You're going to get one with hangs. That's where, things that cause it to hang. And then the queue is anything that it hasn't been tried yet, the next things that it will test. Inside this crashes folder, you'll find a lot of files in this format. It's a bit of an annoying format to type, but what you see here is like every crash gets an identifier, and then there's the exit signal that it got when it crashed. It's what was the source branch, and then what kind of operation it was doing, and on which bit it was working on. Because if we go back here, we can see some of the strategies that it's using down here. So it can do bit flips, byte flips, arithmetics, known-int, dictionary, and then havoc, which I guess is just moving things around, and then trim at the end. So it's doing all kinds of stuff there. Once we've found some crashes, we want to triage them, figure out what are these crashes actually. What I normally start doing is then I compile the binary once more, but without AFL, just with a normal compiler. And then I run the test case with the normal executable. Which, of course, if it doesn't crash there, then it might be something with the fuzzing setup that's causing it to crash. But oftentimes it will crash with the normal binary as well. You could use something like address sanitizer or memory sanitizer and run it through there to see what's going on. Or you could even use GDB, and there's a plugin called Exploitable, which is a nice plugin. If I have time, I'll show you that one, which we can use to figure out if this is likely to be something that would be exploitable from a security perspective. Something you can also do here is use team-in once more. You can use that to minimize the test case. So if you have a large file, maybe you want to make it a bit smaller before you start to or submit it to your set of test cases, or report it to whoever wrote the code. So profit, well, if you're fuzzing your internal binary stuff that you're building yourself, of course reporting it to the dev team, or if you are the dev team, fix them and add them as test cases to your application. If this is external software, well, you might want to do some kind of responsible disclosure. I was hoping for this conference to be able to present some of the stuff that I found, but none of it has been fixed yet, so I can't really talk about that, unfortunately. So I'm going to do a short demo of AFL. So what I've done before you guys came in here is that I've downloaded AFL and compiled it. I've downloaded a tool called SAS-C, which is a SAS to CSS converter. And I've downloaded the stuff that it needs to run or to compile. So I'm just going to compile it first, or before that even. I'm going to, here you can see my current settings up there. AFL hardening is set to 1, AFL instrumentation radio is set to 100, and then I'm using the C-length fast compiler. So I'm going to compile it now. What you'll see here is that it's except from all these warnings, you'll see that it says, maybe I can pause it a bit. You'll see that it's actually, you can see that it's using the correct compiler, because you see here LLVM pass and then the version of AFL. So you can see that it's printing this AFL C-lang fast down here. And it will also say how many instrumentations it was adding. So you'll see that eventually. So now I'm just compiling it normally, just like I would with any other compiler. And it shouldn't take too long. What I've also done is in this GitHub repo that I downloaded, there was a set of test cases. So let's see, do a clear to get it up on the top. So if we look in my current folder here, I have, I'm actually there is a SAS spec, which is a list of test files. And there's a lot of so-called SAS files in here. So I just picked a set of those. I picked those that were in the basic folder, and I put them in a folder that I've called corpus pre. So in here I have a set of files. Now I want to shorten that list and compress it a bit. So I'm going to use AFL C minifier and like this. So I'm pointing it to the corpus pre folder. That's the folder where I have the test cases. I want it output into the corpus folder. then dash dash, and then this is the binary, and it just takes a file like this. It doesn't take any other options, or it doesn't have to. So I can do like this. So now it's going to look through all of these files, and it's going to try to figure out which of these files have similar branches, which of these files are actually giving it something new, and try to reduce the number of files that it needs or that it recommends that you use. As you see, this takes a little bit of time, but it's definitely worth it for later, because we don't want it to sort of run through all kinds of stuff all over and over and over and over again. And the inputs and outputs that I gave it, or the parameters that I gave it, are exactly the same as for AFL fuzz. Yeah, there are 66 files, and you can see it still takes a bit of time to run through it, even though it's fast enough binary, I think, but it takes a bit of time just to work itself through all of these. So for those of you who don't know what Sass is a way of writing CSS, but you kind of compile it to CSS so a browser could understand it. But you write it in a more dense format, and you can have functions and things like that inside it. So you can call a function, and then that would output some new CSS. And this library has been fuzzed many times before, and people have published results from fuzzing it before. So maybe we'll find something, maybe we won't. We'll see. I know of at least a couple of crashes that I found before, so I can show you just how that looks because I have them in a folder here. Should be finished soon. And now what it's going to tell us now is how many of the files that we originally had that it needed. So it took away only 5 of these. So that was a pretty decent set of test cases, actually. The next thing that we want to do is to use a tool to figure out how much CPU, how many fuzzers should we run. And of course, AFL comes with a tool for this. So AFL got CPU. We run this, and it says, well, 4 of your cores, they are already busy doing stuff, because I'm running a couple of fuzzers already on this server. But I have 4 cores available as well. So core 6, 5, 4, and 7 are fuzzers that I can use. This is pretty practical, so you don't end up running stuff and then everything goes slow, and then, yeah. Instead of starting them all one by one, I have created a small script here to start them, because I want to run them each in a screen. So I can disconnect from the server at any time, and they'll keep running. So I'm starting a master fuzzer called fuzzer1, and then I'm starting 3 slaves, fuzzer 2 and 3 and 4. And I'm pointing it to the corpus. This is where we just now minified all the test cases into that folder, and it's going to store its output in output. So let's start this. And now we can go in and look at the first fuzzer. Now we get back to this screen. I'm going to show you a couple of things that's important here. You can see that it's finding paths up here at the right side of the screen here. If it doesn't find paths, that might mean that you're running against the non-instrumented binary. So you might want to go back and double check if you're actually running it against the binary that you compiled with AFL. You should also see here, last new path. If this one keeps just going higher and higher, that might mean that it either already found all the paths, or that you're running against a non-instrumented binary. As you can see in this case, it's finding a lot of new paths. You can see down here, as I mentioned, here you can see the strategies, and you'll see which ones that yielded new paths. Here you'll see the execution speed. Generally, that should be pretty high. We'll get back to some optimizations. And you'll see the total executions as well. Up on the right here, you see cycles done. That's how many times has it been running through all the paths that it's found. And you usually want to stop fuzzing or wait with stopping until it's been running a few cycles, or maybe multiple cycles, because you might run it through one cycle, but then it's going to find new paths the next time around, because it's got a new set of test cases for it. So that's it. But that's not the easiest way to figure out, because now we're running 4 fuzzers, not just one. And of course, the guys who made AFL have thought about that as well. So we have a nice little command called AFL what's up. And we just point it to the output folder that all the fuzzers are now using to synchronize. So we can do like this, and then we'll see the output for each fuzzer. Fuzzer 1 is doing this, fuzzer 2 is doing this, and we can see the speed of each fuzzer. We have a summary down here. So this is the amount of executions that it's been running so far. So we'll just leave that running and come back to it in a while and see if it's found anything. And if it hasn't, then I'll show you some samples that I already have. So optimization. We really want the fuzzing to be as fast as possible. And we also want it to crash as fast as possible if there is something wrong. So anything that we can do to make it crash, if it tries to do things that it shouldn't, if it tries to read outside a buffer, if it tries to write outside a buffer, if it tries to read or write stuff that is already freed, etc., we want it to crash. We want it to be fast. So the first thing we do is, of course, to use these tools to minimize the test cases. And if we have large inputs, we generally want to try to remove stuff if we can, because it's going to be slow. In some cases, we might want to isolate the code that we're testing. Let's say we have a large application, and the code that we're really interested in fuzzing is just a tiny part of it. Maybe we have a parser of some kind somewhere in the code. We can break that out and just write a small wrapper around it and then test that instead, so we don't have to like bring up the whole system if that's a big thing for you. But the LLVM mode comes with some clever tricks here as well. What AFL will do is it will try as good as possible to start the binary, and it will find a point in time where it thinks that, okay, this is where I'm going to start fuzzing from. And then it will make a copy of itself, so it doesn't have to do the initialization again and again and again. But you can help it and tell it where it should stop if you want to, by adding this. This will tell AFL that when you come to this point, this is where you can make a copy, and then for the next execution, you just use this piece of memory and then run it again. So you have a fork server, basically. You could also use something called LLVM persistent mode. And this is something that can be useful for, let's say you have an application that takes a really long time to start up, and then there's a small piece that you want to test, but you can't really isolate it in any clever way. You could do something like this. You can add a loop to it, and then you have to make sure that you read the input data, do the stuff that needs to be fuzzed, and then you reset the state cleverly inside there by yourself. And this will make it a lot faster, of course, because now we can do a lot of fuzzing on a single process. AFL also comes with something called a libdislocator. Libdislocator is a drop-in for the libc allocator. And what it's going to do is quite clever. It's going to add these guard pages around everything that you allocate in your code. So if you allocate a piece on the heap, it's going to add a guard page. So it's going to allocate it just next to a guard page. So if you try to read outside this piece of heap that you've allocated, it's going to crash because it's going to hit the guard page. Similarly, if you free something, it's going to mark that as a guard page. So you can't really go back and read something that you already freed. And so it adds a lot of these things to your code. The problem with using libdislocator is that a lot of binaries, they just won't work when you add it because, I don't know, they're doing things that they shouldn't already. So when you try to start AFL with libdislocator, it might just crash immediately. And it's just going to keep crashing. Or it's going to say, I can't really start this in a proper way because it keeps on crashing. But it's a clever, it's really useful for applications where it actually works, and it probably works for a lot of things. I just had it crash a lot lately with things that I've fuzzed. So I've had to run without it for some time. You can also add dictionaries, and this is an example dictionary from the GitHub repo, where you can add stuff so it doesn't have to discover everything itself. So you could either have a directory full of files with tokens in them, or you can just have a single file with key value pairs. And generally, it's going to ignore the names. It's just going to use the values. And you can hex encode stuff that's not ASCII, so as you can see at the bottom there. So this can also help it to become faster. So when I'm now fuzzing this SAS compiler, I could have added stuff that was common in a SAS or CSS file to help it along. This can be useful if needed. So fuzzing is not an excuse for writing bad code, of course, but it might help you detect that you've written bad code, or that your colleagues have written bad code, or that someone else have written a bad library. It can be useful to maybe fuzz libraries that you have, fuzz your own code, fuzz things that, just generally fuzz stuff. It's fun. This is a slide from Patricia Aas. She did a talk at NDC Oslo called Secure Programming Practices in C++, where she brought up a lot of things that we should do, and one of them was, I'd really rather you didn't use pointers a lot. And I've fuzzed quite a lot of applications, and I've seen a lot of, as I said, I'm no C or C++ programmer, but I've seen a lot of code that looks kind of iffy when you look at it, with lots of pointers and things going around, and then you see like more modern C++, like Patricia is recommending you write. And when I fuzz these things, I generally find, of course, a lot more bugs in the pointer code stuff than in the properly written C++ modern stuff that she's recommending. So there's a big truth to this. So let's go back to the fuzzer now and see what's going on. It might not have found anything. Probably not, because it hasn't been running for a very long time. So it says our fuzzers are still alive, but it hasn't found any crashes yet. OK, of course, I prepared for this. So I have a folder here called output2, which is a folder of some crashes that I found earlier. So we have all our 4 fuzzers here. Let's go into fuzzer 1 and see what's going on in there. We'll see that in the crashes folder, there are a good set of crashes in here. What you see all the way to the bottom here is a README file. What that file tells you is what kind of command was being run when you were creating this crash. So you see here, this is the command on the center of the screen. So you can easily, OK, what was I doing when I found this crash? OK, I was running the fuzzer like this. OK, that's fine. So let's look at one of these crashes. So there, it looks like kind of a normal file. The thing I'm reacting to here is that there's like a variable and then a percentage up there that looks a bit odd. And it says there's a flip of something in an early place in the code. So maybe there's something wrong here. Let's see. So I mentioned exploitable. So what we can do then is we can open up the binary in GDB. And then we can run it against this. Let's see if I can find my mouse pointer. There it is. We can run it against this file. And it's in the output2 folder, like this. And we run it, and we see we get a segmentation fault down here. What we can do then is to use this so-called exploitable plugin for GDB. So I have that lying around here, of course. You can download it from GitHub. It's a bit, let's see here. It's a Python script that you just import like this, and then you can run exploitable. So that tells me what was happening. It's an access violation during a branch instruction, and it says exploitability classification exploitable. So this might be a good find for someone who wants to attack this binary. Of course, this is a binary that you usually run locally on your server, so it's not really a big problem maybe, but if this was like an image parser or something that would parse data coming in from a network, that might be a big problem. So see what's going on now. Did it find anything? No, it didn't. OK. This is generally the way I use it. I set up the fuzzers, and I go in and check regularly to see what's going on. Of course, now it's just been running for a short period of time. But if it was running for, I usually leave it running for quite a few days to get the cycle count up. I'm going to show you one more thing. If we go into one of these slave fuzzers, they might have found more paths. Let's see, compare this. This one has 3,000. This one has, let's see, that was the same one. Sorry. Oh. There we go. So this one has over 4,000 paths. So they're doing a bit, working a bit in a different way, or doing different type of fuzzing strategies. So, or in a different order. So it might find things faster. And usually you'll see that the slave fuzzers, they will cycle faster because they're not doing the full thing, while the master fuzzer is trying to go through everything, and it will generally take a lot longer to go through one cycle. I normally wait until the master fuzzer has been running for maybe 5-10 cycles before I quit. While the slave fuzzers, they might have run like 40 cycles or something like that. Generally, you want the execution speed to be quite high. So 1,000 executions per second or over 500 executions per second, that's fine. Actually, if you run something that's really slow, AFL will tell you, and it will be like a snoring sign next to the execution speed, and it'll say this is a slow binary. It will actually say so under startup as well. So what I'm hoping by doing this talk for you is that this will get you into fuzzing, and I hope I've shown you that it's not really that hard to get started. It's actually quite easy. I was kind of surprised because you don't have to know that much to get started. That's what I was dreading when I first oh, I'm going to start fuzzing, but I don't know anything about it. What do I need to know to start? And it's not that much. Some resources that you might find useful. There's a blog post from Foxglove Security called Fuzzing Workflow, a fuzz job from start to finish, which kind of goes through the running the minification of test cases and all that kind of stuff. And there's 2 good talks from one from RURSEC this year, and one from Craig Young, the one that I quoted earlier, which is from 2016. And these, at least the B-sides talk, it goes a bit deeper into how the instrumentation works, while the one from 2018, it actually explains how you can fuzz Windows binaries and not just Linux binaries. So, in summary, I think fuzzing is quite easy to get started with, and it can be really useful for making robust applications. And if you're fuzzing other stuff, it might even earn you a bug bounty. Questions? Yes?
Yeah, the corpus folder you set up initially.
Yep.
Do you always need the input files, or is that just for convergence? What's the content of the input files you're using?
Yeah. So the input files I was using are actual files from the test cases for the binary down testing. So I went to the GitHub repo, I grabbed a set of test files, and I used that as an input. And that kind of primes the fuzzer, so it makes it start fuzzing properly sooner. But you could have used like a hello file, like Michael did with the JPEG parser. You could just use like an empty file if that's what you need. But it's generally better to have a good set of test cases, because that makes it, or puts it faster into a place where it can start finding stuff.
Yeah, but do you really need input file for every application you want to fuzz?
No. You could, but I mean, the way AFL works is that it takes some input and sends it into the application, and then sees what happens. So you need some way to like invoke the application, and that's usually through a file or through standard in. So if you're fuzzing something, I don't know, if you're fuzzing something where you can't like give it a file or give it some input and make it process it, then it might be a bit harder to fuzz it.
For that, on that comment, libfuzzer from client can work without files. You can write a function that generates corpus for you.
Right.
Okay.
So there are other smart fuzzers than AFL. So I'm introducing AFL here, but there are a lot of other fuzzers as well, and some of them are faster at doing other stuff, and some of them are. You might find a case where they're much faster than AFL, for instance.
Yeah, for instance, OpenSSL luckily can be found under, I think, under a minute or under 2 minutes with fuzzer.
Michael, I think it was Michael Saluski who went back after both, or at least after Heartbleed, and figured out how they could have found Heartbleed using fuzzing, and then without actually knowing anything about the heartbeat functionality that caused Heartbleed. But it wasn't found originally using AFL, but it could have been found.
Is it relevant to run fuzzing tests as part of your build pipeline as regression tests, or is this something that you do completely detached in the middle of the night?
I would do it, or I wouldn't run it as a part of a normal build pipeline because it takes a lot of time. So I would rather say this is something that you fuzz binaries at a pace, like once every. It depends on how long it takes to get enough cycles, but maybe you fuzz every. If you're releasing a new version every day, you can't fuzz them all because it might take more than a day. It might take a week to fuzz properly. But like I would just continuously fuzz. And then when I release a new version, I would wait a bit because I want the previous fuzzer to start, but then I'll start fuzzing the newest binary from there on. So it's something I would do continuously, but I wouldn't do it as a part of a normal CI pipeline. Other questions?
Yeah, on that, how, if I wanted to go faster, is it the total runtime to get a decent fuzz if I add twice as many cores and then have twice as many slaves? Does that mean that I would move half the time spent on doing the same kind of fuzz, or is there some overhead in the master that would make this?
I think if you go to Craig Young's talk and look at towards the end, he has some statistics from stuff that he's done to optimize stuff, where you can see that he at least gets double the speed and more than that. But it will take, well, it depends on the size of the binary, the number of branches. Like there's no good answer. Sorry. Yeah.
Between the fuzzers running different cores, how well organized is it so you don't fuzz the same case twice?
So how well organized are the fuzzers when you run multiple of them, so they don't run the same case? Well, I think they're pretty well organized. I don't really have a good answer for it, but it seems to me that they find different crashes from the different fuzzers. So it seems to work pretty well because they're using this output folder as a sync folder. So they kind of write stuff there for the queue and then they pick stuff out. You could even, I've seen setups from this where you can run it across multiple nodes. So you could have, but then you have to copy the sync folder or sync the sync folder basically between the nodes at a certain pace. But there are scripts for that as well. I have never tried it. I've just run it on a single node.
How feasible is this to run non-C or C++ binaries? So for instance, if I want to take Java and I can put the instrumentation into that, is it possible to fuzz a non-native binary or something with a virtual machine if I port the instrumentation?
I'm not sure. When I got into this, I started because of this training where they were fuzzing Node.js native binaries. So it's actually there you had what I would do then is I compiled Node.js with instrumentation radio set to 0. Because you need to compile it with AFL, but then you don't want to instrument Node itself because I wanted to actually test these libraries. So what I did then, I compiled Node.js, and then I had a small JavaScript that was just like pulling in a file and calling the library. And then I compiled the library itself with AFL, but it still was C and C++. So I don't know if you can. You could probably fuzz Java itself, but I don't know if you could fuzz like a Java application because I think you would still fuzz the runtime and not the actual application. I don't know if that answered your question.
No, it was just. How does so that then raises the question: how does the instrumentation tell AFL what's happening? Because if you can fake that bit, then you can fake it from anywhere.
Good question. I don't actually know the internals of AFL. So yeah. Any more questions? Yes.
Another question is hypothetically what you're saying could be possible with LLVM.
Okay.
Yeah, it just seems like would then
Mm.
broaden it out to the whole area because fuzzing is not specific to C++ or C.
Yeah.
All right. Thank you for coming.